All right, so we're going to do a little more work with iterated integrals today. And what we're going to concentrate on today is we interpreted iterated integrals as the area of a plane region, or we found the area of a plane region with an iterated integral. So we're going to do a little more work with regions and how those relate to the integrals and their limits. So just a quick recap. So if we're finding the area, so if we talked about two different cases. If we had the area and we're finding the area bounded by two functions of x, something like this. And this was g1 of x and g2 of x. We call this vertically simple because we set up representative rectangles that are oriented vertically. And first we integrate to find the area of one rectangle, and then we integrate over the region from left to right to find the area of all of them added up. And we said the area of this region was the integral from a to b, the integral from g1 of x to g2 of x of dy dx. And we call this vertically simple. And then the second one is if we're bounded by functions of y on the left and right. So we have something like this. And we'll call these functions h1 of y and h2 of y. We said the area of this, we called this a horizontally simple region because we set our little representative rectangles to find our area horizontal. And we said the area of that region would be the integral from c to d, the integral from h1 to h2, dx dy. And with an iterated integral, we can always, depending on the region, we're going to want to pick either vertical rectangles or horizontal rectangles. We can pick either one, and our answer should come out the same. A lot of times, picking one is much easier than picking the other orientation. And sometimes, depending on if we have, rather than just the area of this region, if we have some surface that's above it, and we'll talk about that later in the week, where we're talking about the volume under this surface, it's going to be easier to evaluate the integral in one order versus the other. And we'll talk about an example of that today. So what I want to concentrate on today is looking at these regions, setting up using a region to set up an integral, and also switching the order of integration. Just a little practice with switching the order. So basically what I want to do is just do a few examples of setting these integrals up, talking about switching the orders, and going from there. So any questions? This is just a recap of what we talked about on Friday. Okay. This multiple integration is one of my favorite Calc 3 topics. To me, it's such a fun way of thinking about how things are oriented and how they're related to each other. So I always really like it when we get here. All right, so let's look at a couple of examples. So we want to find the area of this region. And this function is y equals 1 over the square root of x minus 1, and we're interested from x equals 2 to x equals 5. So we want the area of this region, and we want to use an iterated integral. So which way is it going to make sense to set our representative rectangle? Sean says vertically. We could set it horizontally. We'd have to split up our region, because if we look at it like so, here we just have a rectangle, but here we'd have different limits of integration, because our horizontal rectangles would be intersecting the boundaries in different ways. So we're going to do vertical rectangles. So I'll erase these little dots.
Why do you have to use iterated integral for this?
We don't have to. We're doing it now just to practice setting them up. And then
But you could
you could use the technique that we used before, because we showed yesterday that after we take that first integral, we get exactly what we did to find an area between two curves before. All right, so we're going to set my vertical rectangle, and there's my little dx. So my area is going to be the integral from x equals 2 to 5, and y varies from 0 to 1 over the square root of x minus 1, and dx is my order. So what's the integral from 0 to 1 of, 0 to 1 over square root of x minus 1 dy? It's just going to be, this is just a constant, so we get y times this constant evaluated from 0 to this value, so it's just going to leave us with 1 over square root of x minus 1 dx. Just like we would expect. And then when we evaluate this is not a hard integral to evaluate. We end up with, the area comes out to be 2 square units. Yeah? We do. But then y varies from, so let me put a note down here. The integral from 0 to 1 over square root of x minus 1 dy equals y over square root of x minus 1, and we're evaluating that on 0 to yes, sorry, this should be right.
Oh, no, yeah.
Yes. dy, that's y evaluated on 0 to 1 over x minus 2. There we go. I got one step ahead. I was putting the square root of 1 minus x. 1 over square root of x minus 1 in.
How does that get the area of the rectangle?
So we're saying this is super thin, and we're taking this rectangle and we're dividing it into tiny little rectangles, and that's dy. With dy from 0 to 1 over square root of x minus 1. All right, everybody good on that? Okay. Let's look at a little more complicated region. Y, x, and this is x squared plus y squared equals 4. Now we know how to find, we already know a really easy way to find this area, but we want to use an iterated integral and see if we verify that we come up with the same answer. But basically we're practicing setting up iterated integrals. Now for this region we could set up a vertical or a horizontal rectangle. My personal preference is to try to set up vertical rectangles. And that's just the way that I usually like to choose these. So I'm going to choose a vertical rectangle like so. And that's dx. So if I choose vertical rectangles, we could choose horizontal rectangles. My area is going to be the integral x equals 0 to 2, and the integral y equals 0 to square root of 4 minus x squared dy dx. So for my first integral, the integral of dy from 0 to 4 minus x squared, what do we get? This is just like the last one. We just end up with square root of 4 minus x squared dx. This is just y, and we're evaluating on 0 to 4 minus x squared. And then to evaluate this one, what do we need to do? This is a trig sum. So draw my triangle over here. Theta x square root of 4 minus x squared, and this is 2. So when I do my trig sub, I'm going to just write, I get cosine theta is square root of 4 minus x squared over 2. Sine theta is x over 2. So x equals 2 sine theta. And dx, for all my substitutions, is 2 cosine theta d theta. So when I substitute this in, I'm not going to change my limits. I'll do my limits at the end. So we're just going to evaluate. We have the integral of 2 cosine theta times 2 cosine theta d theta. So we end up with 4 cosine squared theta d theta. And do we remember the trick for evaluating the integral of cosine squared theta? 1 plus cosine 2 theta divided by 2. Remember, so we're going to, when we start doing polar coordinates and spherical coordinates, this integral comes up a lot. So we need to remember that little trig identity. So this equals 4 times the integral of 1 plus the cosine of 2 theta divided by 2 d theta. And when we evaluate that, we get 2 theta plus sine of 2 theta over 2. And now we need to figure out our limits. Our limits are x equals 0 to 2. And x equals 2 sine theta, so when x equals 0, theta equals 0. And when x equals 2, sine theta equals 1. I'm using this to change my limits of integration. So theta equals pi over 2. So I'm evaluating this on 0 to pi over 2. And what should I get when I evaluate this integral, just based on what we know about this region?
1/4 pi.
Our radius is 4, so we should get 1/4 pi r squared, or
1/4 radius.
the radius is 2. So we should get pi. When we evaluate this integral, this over the limits, we do get pi. Just like we would expect. Now, a little later on, we're going to talk about doing double or iterated integrals in polar coordinates. Polar coordinates would be much easier to do an iterated integral for this region. Questions on that example? All right, let me do. I'm going to do one more like this, and then one a little more complicated example, where switching the order of integration makes. I think we're okay. For this one, we're just going to set up the integral. We're not going to evaluate it, I just want to set it up. So we want the area of the region bounded by y equals x, y equals 2x, and x equals 2. So sometimes they'll give you a problem and say find the area of the region bounded by these things. So the first thing that I suggest doing is sketching this region. So y equals x is here. Y equals 2x is there. And x equals 2 is there. So we want the area bounded by these equations. So we're looking for this area of this little triangle in here. Which way are we going to want to set and we're using an iterated integral, so which way are we going to want to set our representative rectangles? Set them vertically. We could set them horizontally. Then our limits of integration would change. We'd have to set up two separate iterated integrals because our limits of integration would change right here. So we set up our vertical rectangles, and our area is going to be the integral. X varies from what to what? 0 to 2. Y varies from what to what? X to 2x. dy dx. That would be our integral. A lot of times students have a hard time thinking about y varying from a function to a function. So that's kind of a key concept and wrap your heads around, is when we're doing iterated integrals, our limits of integration can be from one function to another function. And if we evaluated this iterated integral, our area turns out to be 2 square units. Everybody good on these examples? I'm just trying to go through a bunch, setting them up. So let's look at switching the order of integration. And then we'll do an example of why we would want to switch the order. So for this example, we have the iterated integral, 0 to 9, square root of x to 3, dy dx. So we want to sketch the region and then switch the order of integration. And remember that the limits of integration tell us about our region of integration. So let's sketch this region. So y is going to vary from the square root of x to 3. If that helps you to remember, you could say that square root of x is less than or equal to y less than or equal to 3. That's what the order of, or that's what the limits of the integration on y tell us. So y equals square root of x looks something like that. Y equals 3 is going to look something like this. So, and x is going to vary from 0 to 9. So I'm going to say these intersect at x equals 9. So which region are we talking about? Are we talking about this region down here or this region over here? The one on the right below square root of x, or the one on the left above square root of x? We're above square root of x because y is going from square root of x to 3. So y goes from this function up to this function. So we have vertical rectangles, and we're talking about this region. So this is my region, R. So the way we have it set up here, we have vertical rectangles, and we're in this region. So we want to switch the order. So we want to change our order to dx dy. Well, if we switch our order, so the area is going to be the integral, and our outer limits are going to be dy this time. So y is going to vary from what to what? 0 to 3. And x is going to vary from what to what in this region? 0 to, if I set my representative rectangle, I'll do it in red. So I set my horizontal represented rectangle. X is varying from 0 to this function. So x is going to vary from 0 to y squared. Y, so we need our function, we need our limit to be a function of y when we set our rectangles horizontal. So we just change y equals square root of x, turn that into a x equals some function of y. So x equals y squared. And then we just switch our order, dx, dy. Not too bad to evaluate either way, but that's how we go about switching the order of integration. We have to make sure we know what region we're in, and 2, we need to make sure that our inner limits of integration are a function of the outer variable. So we switch from a function of x to a function of y in this case. And sketching the region, and sometimes when I do these, often I'll draw the little rectangles just so I make sure that I get my limits, that I'm sure I understand where my limits are going between them. Questions on that example? All right, let's look at one last example of why we want to. Here, the switching the order really didn't make that much of a difference in terms of the evaluation. Let's look at an example where switching the order does make a difference. We'll talk about where this next kind of problem comes from on Thursday. So we have the integral from 0 to 2. We have this iterated integral from x to 2 of e to the minus y squared dy dx. Now, the way we are going to interpret this is e to the minus y squared is some surface that's up above the xy plane. And we're trying to find the volume of this surface bounded by this region in the xy plane. Well, do we know how to evaluate the integral e to the minus y squared dy? can't do a U sub. We don't have anything to do integration by parts. We don't have another part here. Turns out that e to the minus y squared, not an easy integral to evaluate. So let's see if we can switch the order and get an easier evaluation. So I'm just going to make a note here. Integral of e to the minus y squared dy is not easy. So let's switch the order and see if that helps us out. So let's sketch our region. X is varying from 0 to 2 and y is varying from x to 2. So here's y equals x. And y equals 2. So y is varying from x to 2. So my vertical rectangles are here. So we want to switch, and it says x goes from 0 to 2. So we want to switch our order, and we want to put our representative rectangles horizontally. So for this order, y is going to vary from what to what? We put our representative rectangles horizontal. Y varies from 0 to 2. X varies from x is going from here to here, 0 to y.
The one on the other side. The one here, y on the outside.
We're switching the order, so our order is going to be dx dy. So x is going to vary from 0 to y, and y is going to vary from 0 to 2. And now we have e to the minus y squared dx dy.
Oh, we have x to the y squared.
Right. So now we
y
can
squared. Okay.
now we can evaluate this integral, because the integral of e to the minus y squared dx is just x e to the minus y squared, and we're evaluating that on 0 to y.
What is e to the next y squared? Like where in our layout, I think it was
So the way we're going to interpret this, and we'll talk more about this on Thursday, is e to the minus y squared. We could think of it as some surface. Z equals e to the minus y squared.
So our picture is what's in the xy.
That's in the xy plane, and e to the minus y squared would be some surface up above the xy plane. And we could interpret this integral as a volume underneath that surface bounded by this region. And we'll talk more about that on Thursday. All right, so now we have the integral, this integral. The inner integral is easy to evaluate. Our outer integral is just 0 to 2, and we get y e to the minus y squared dy. And now we have a nice u substitution. So the integral of y e to the minus y squared dy equals what? -1/2 e to the minus y squared. And you're evaluating that on 0 to 2. And this comes out to be 1/2 1 minus e to the minus 1/4. Actually, is it minus 1/4 into e to the minus 4, right? When I evaluate it at 0. E to the 0 is 1.
Say minus 0?
Yeah. It would be e to the negative 1 minus 1.
So let's write it out.
Or minus 1 half.
Let's make sure. So we get minus
Over the
1 half, and then I get e to the, when I evaluate this at y equals 2, I get e to the minus 4, minus, and I evaluate this at 0 minus 1. I distribute the 1 half, so I distribute, the way I wrote it is 1 half, 1 minus e to the minus 4. All right. Everybody good with that one? Questions? So switching the order of integration is going to be an important tool that's what we're kind of working on developing today, is switching the order. Visualizing the region and switching the order.
So why do you iterate
So on Thursday, so what we're doing today is just practicing setting them up. On Thursday, we're going to talk about when we have an integral like this, where we have some function along with our iterated integral. So we're not just evaluating dx dy or dy dx. We have some function dx dy dy dx, and then we need to be able to do those iterated integrals. What we're doing today is just kind of taking like our first steps in practicing doing it. All right, other questions? Okay, homework. There we go.